Welcome to my brief tutorial on using the CPA diffusion in tissue program I developed. There are definitely other ways to do this, other methods out there, but I found it useful to do the following, and maybe you will too, so I figured I'd make this video. So here's the basic idea. We're trying to cryopreserve some system, some tissue system, and we're asking the question of what happens to the CPA concentration in this sample as time goes on, and as a function of the extracellular or surrounding CPA concentration, this surrounding solution here. And the way that I'm modeling it here, and the way that the program I'll show is modeling this, is that it's a long cylinder, or that's one way, but this is actually going to be for a plane wall of 1.2 millimeters thickness, so one-dimensional diffusion, and just one-dimensional diffusion in through one side here. And so we can test different profiles. I'm giving you a sense of that here. There's this gray profile versus the black profile. The ordinate here is the CPA concentration, which is a percent of the max CPA concentration. So 100% means undiluted CPA solution. And what's being shown here is that this gray profile has less time at the final CPA loading step than the black profile. And so when we do run the program, the result we get is that as a function of distance within the tissue, so as x increases here within the tissue, we get this decline in CPA concentration at the end of the final CPA loading step. So that's either here or here. We get a rather low CPA concentration near the plane furthest from the CPA solution, and equal to the surrounding CPA solution at the plane nearest to the surroundings. Okay, so how to get this program, how to run this program, I'll go over that next. So to download the program, you can just go to my GitHub profile. And click on the, not this one actually, click on the exposure to CPA tissue link. And then there are two options here. One of these is going to be for a model of a plane wall, and then the other is going to be for a model of a long cylinder. So think about which model fits your system best. I'll just use this one. And then you can download it here. It's a Mathematica program, so you do need Mathematica installed on your machine to run it. For more information, you can look into this program here, in which I benchmarked the results that I was getting compared to a published result in the literature. The solution process is the same as in this as this. This just has some more features, some more outputs. All right, so after you download this, here is the way to understand this. So in this program, there is one big section, which includes an input section here, and then various output sections. And at the end of that, there are these tables that are not appearing right now because you need to click enable. This content is safe, so I'll click enable here. And so this is the ultimate output. And the way you can customize this code is as follows. You can basically follow the instructions here. I'm not going to go over it. All of them I'm just going to go over, like, some variables that are the least straightforward to use. And essentially one thing to know is that when there's grayed out text like this, that means it's been commented out. So to comment out a section of code in Mathematica, you use these symbols. And the way to, say, customize this is If you want to test a different CPA profile, you would change the inputs within this profiles variable. Right now, there are lots of profiles inputted, all but one has been commented out. So within this, there's, one profile here, another one here, another one here, and so on, all testing different things. Here's the format with which you can input a profile. So the first argument within each profile is the surrounding CPA concentration over time. So that's the first one. And then the next one is the surrounding temperature in units of Kelvin. So this is 4 degrees Celsius. And then the final entry is the location of the final CPA loading step. So in this case, it is the 5th step here. The first entry in each of these steps is the CPA concentration in units of percent. So 0% of the max CPA concentration, 20%, and so on, all the way up to 100%. And the final CPA loading step, this designates the location of the final CPA loading step. You could put it somewhere else if you wanted. And there's actually a compelling reason to do that. So if you, say, wanted a step here like this, this could actually lead to less overall damage and better outcomes. I mean, you'd probably want to tweak some things, but at any rate, you can look at the 2018 Benson and others paper for that information. But at any rate, using the more conventional thing, which is to have the final CPA loading step as the place where it's 100%, we'll keep that entry at 5 here. And the second entry in each of these steps is the time in units of seconds. So this is 5 minutes, this is 10 minutes, and so on. So this goes from 0% to 20% CPA. And this actually will get processed in a way such that it's going to be 20% CPA between 5 and 10 minutes. That's not what's literally displayed here. I think for it to be more literal, you could think of it like this. So 20% CPA between 5 and 10 minutes. But the correct way to enter it is like this. All right, so that's how to understand what's being entered here. I'll just leave it like that. Next variable here, this refers to the position within the tissue. So an entry of 0 would be the plane furthest from the CPA solution. That could be the center of the tissue. And an entry of 1 would be the plane contacting the CPA solution, the boundary condition. And then you can enter various things in between, if you want to know what it is like at this one or whatever, you can do that. Yeah, you can get rid of everything and so on. And then this next entry here is the thickness. So this is one-dimensional CPA diffusion. The program is not set up to do anything more than that. So this is the key geometry parameter here. And you can test multiple different ones. So here it's set up to test multiple different ones. If you just want to test one, these are all in units of meters. If you want to just test one, which is 1.5 times 0.001 meters, you could do that. Otherwise, you could test multiple, which is going to be consistent with the results I'm going to show. And then here is how many sides of the tissue are contacting that CPA solution. For a plain wall, it kind of only makes sense for this to be 1 or 2. So enter 1 or 2. And then these next things are if you want to be able to export this data. I'll just leave this at 1, but if you want to be able to, if you don't want the program to output this, if you want the results to be, if you want to look at less output, put 0 for this, otherwise just leave that. And these are related to the data it's going to output. Yeah, and then some system-dependent things are here and here. So this it represents the desired CPA concentration. This is going to be the minimum CPA concentration that achieves ice avoidance, as the definition I use for that desired CPA concentration. This is a rather simple way to evaluate this, because if you think about it, the desired CPA concentration is going to be dependent on where you are in the tissue, because presumably when you actually are cooling and rewarming the tissue, it's not all cooling and rewarming at the same rate. There's some position dependence there, and so the center of the tissue in a lot of cases would actually need more desired CPA concentration, so this would not be a constant, but just treating it as a constant in this program, I've just estimated it as about, you need to load the tissue to at least 90% throughout to avoid ice. And then the rest of these are parameter values and stuff that is needed to generate the output. So going through the key parameter value here, it has this equation in terms of temperature right now, because it is set up for that. What I actually ended up doing when I was running it is I just set it as a constant. So you'll notice there's no capital T here. There's no temperature dependence. It is set up so that you can add temperature dependence if you want. You can, uncomment this and uncomment this, and then uncomment this one. And you should be, not overwriting it with that. And that way you would have these diffusion parameters as a function of temperature. I didn't design this code to handle different temperatures in the profile. It's maybe something someone else can do. So this feature I don't think is super useful right now, but especially if you know these values, then it could be good to just input them and structure it that way. So yeah, that's really the key parameter value, the key thing to go with, to think about. The rest is just the solution. And this code definitely can take a while to run, so I'm not going to run it. I'm just going to show you the results I got when I did run this. So this is the input. You can input multiple profiles. For this time when I ran it, I just inputted one profile. And the first output actually is kind of consistent with the sidedness input. So if it's two-sided CPA diffusion, it's going to output this as 0.5 times the characteristic length. Here it's outputting thicknesses 1 times the characteristic length. So that's just a quick check so that you can look and see whether it's giving you an expected result. If it's not, you can just hit Alt period to abort real quick. So yeah, that's the profiles being used, and we entered 3 different positions within the tissue and also 3 different total thicknesses. It's going to output a lot of data for that. A lot of this, if you want to, you can just Control C, Control V in some program like Prism to plot this somewhere else, but I'll skip to the end here to kind of get a sense of what's happening. So here's some plots where it's combining all of the information. So this is CPA concentration over time. If you remember that profile, we went up in concentration initially and then stepped back down. So the CPA concentration over time is making sense to me. The red curve is the thinner tissue. We would expect that curve to reach a higher CPA concentration faster and to reach a CPA concentration at the final loading step that is higher, given that the system never reaches steady state. Since this is a transient process, that's quite expected. And then for that red curve to fall faster than the other ones seems rather expected. So that's the concentration versus time plot. And then we have a concentration versus position plot here. Similar sort of thing. The CPA concentration in the thinner tissue, the red one, we would expect to be higher at the end of loading, which is this time point here, consistent with whatever you inputted as your final CPA loading step. And then here's just this first table is just a quick check, give you a sense of what the estimates are for this sort of thing. All we're doing to estimate the diffusion time is the simple formula of 2L squared over D in this case. So that can just give you a quick comparison point. but the uh, the bulk of the work the program is doing is calculating the information in this table here, which is related to the plots I'm showing. The plots are from the uh, the program's more substantial calculations, in which it's comparing, in this case, three different thicknesses, so 0.75, 1.2, and 1.5. It's comparing them at different positions, 0, 0.5, and 1. This is 0. It's going to be further from the CPA solution, so we should see a lower number here, which we do. 84 is lower than 99. This is nearest the CPA solution. So that's all making sense. And what it's basically able to do here, which I think could be quite useful, is it's able to predict how much time you're expected to need to reach the desired CPA concentration. So for what was inputted, which was 90%, and again, you can change this to be a different constant value, it's going to give an output here of you need 6 minutes to reach at least that much everywhere in the tissue. If your thickness is this, if your thickness is higher, you should be loading for 18 minutes. If it's still higher, you should be loading for 30 minutes in this case. And then here's what happens if we didn't do that, and we used a profile which we used here in sample 3 that had a lower time, 25 minutes. So this 25 is less than 30, right? Since 25 is less than 30, we would predict ice, which makes sense because this at this position, far from the CPA solution, it's 84% loaded, and we need at least 90% loaded to predict that it's not going to form ice. And just to understand this rightmost column, if it predicts ice somewhere, it's just going to predict ice anywhere in the tissues. That's why it's yes for all of these entries. Yeah, and that's how to understand the program, which hopefully gives you a sense of how you could customize it yourself.